Alrighty. Good evening, everyone, and welcome to the August edition of the meeting of the Ottawa RASC. A special welcome to all members and visitors. Just a reminder that we are recording this meeting for future viewing. Please use the Q&A to ask any questions to speakers. The chat box comments will be seen by all. We've disabled the raise your hand feature. The RASC Ottawa Centre acknowledges the trust placed in us by our First Nations with their ancestral lands and sky. All right, so we've got an action-packed program for you tonight. You'll be stuck with me for a little bit for this introduction, as well as Ottawa Skies for August. Then we will have Mr. Tim Cole giving us a talk on the discovery of helium, followed by a presentation by Andrea Girones on solar observing in 2023. We'll take our break, which includes our AstroTrivia question. Then we'll follow up with Rick Wagner on a presentation on photometry and light curve analysis. Then we'll hop into our observation reports and the monthly observing challenges, and we'll close up with some announcements. Welcome to all our new members this month. Thank you all for joining, and we hope that you enjoy being part of this group. We've had so far 54 new members in 2023. We've had a couple members in the news this month, Jerry Gruber, myself, and Andrea. Yeah, so we lost Jerry Gruber there. I don't know a whole lot about him, but may he rest in peace.
Just to pitch in, Oscar, he just passed away in the last day or so, so we have no further information or details. But Gordon Webster, our astronauts editor, who knows him much better, will say a few words next meeting and likely have some material in Astronauts next month.
Thank you, Chris.
I can take over the next slide to save you an awkward situation, but it's
Please.
Great to see our members being recognized for their astroimaging skills. So here's Oscar receiving his Astroimager Deep Sky certificate. So congratulations.
Thank you. It would have been awkward to be congratulating myself. So thanks for sparing me. All right, and Andrea had her Aurora images on CTV News. Congratulations, Andrea. As it looks like it was also picked up by Fox Weather.
And it's neat to see that they picked up on the Barbie theme in her pink images. How well did she do to coordinate that?
All right. So as a membership benefits for joining the RASC, you can join us as a regular member for $103. Family memberships $97.50 plus some, depending on how many folks you are in your family, and $62.40 for youths. Membership gives you access to the Ted Bean Lone Library, the Fred P. Lossing Observatory, and our wonderful Stanmont Library. You also get access to the RASC Journal, as well as the yearly publication of the Observer's Handbook, and also the wonderful Astronotes that are edited by Gordon Webster. But most important of all, you get access to a wonderful community and all of our members, presenters, and speakers. All right, another membership benefit is the annual dinner meeting, which I'm in the midst of planning. We will be bringing it back this year after a 3-year hiatus, I suppose, due to COVID. It's being planned for either the second or third week of November, the Friday evening in those weeks, depending on availability of speakers and venues. I'm currently speaking with Algonquin College who have been traditionally our hosts for the annual dinner meeting, as well as I'm reaching out to some speakers. I'm having a little bit of tough luck with the speakers that I had in mind, so I'm still poking around. If anyone has any ideas for speakers for the annual dinner meeting, please feel free to reach out to me, vice-president@ottawa.rasc.ca. All right, I'm going to jump into our Ottawa skies for August, put together by Dave Chisholm, who's not with us today. All right, so the new moon this year is on the 16th. And we have our full moon on the 31st. The Perseid meteor shower peaks the night of the 12th into the morning of the 13th. Look northeast at 11 p.m. This is a really nice annual meteor shower. Hopefully the skies cooperate with us. But being Ottawa and having an astronomical event at the same time as good weather is a rare phenomenon. So let's keep our fingers crossed. All right, so days are getting longer as we go closer to the fall. You can see the sun rises at 5:47. Sorry, they say days, nights are getting longer, excuse me. 5:47 in the morning, August 1st, and that gets delayed to 6:23 by the end of the month. And sunset comes earlier, moves from 8:31 to 7:43 by the end of the month. Mercury, visible some portion of the evenings. August 10th is the greatest eastern elongation. It'll be about 27.4 degrees east of the sun. It's best viewed. It'll be at its highest point above the horizon in the evening sky. And you can look for it low in the western sky just after sunset. Venus is visible in the early evening for the first half of the month, and Mars also visible in the early evening. Jupiter visible late evening and through the night. Saturn visible in the evening. And Saturn's up at opposition on the 27th. Uranus is visible in the evening and through the night, and likewise with Neptune. And here is our cartoon of the month. It looks like someone may have taken a photograph of me and turned it into a cartoon, I guess. That's what I look like sometimes when I'm trying to image. All right, and without further ado, I shall hand the reins over to Tim Cole to give us a presentation here on the discovery of helium. Tim, take it away.
Tim's going to display from his own computer, so I'll stop sharing the slides.
Am I here?
Yes.
How come I can't see my screen? Okay. Okay, that's better. Okay, well, welcome everybody. Happy August and all. If you do a reference search, you're going to find articles from very respectable sources, such as Britannica or the Smithsonian Magazine, I'm just picking two, that will inform you that helium was discovered independently in the sun spectrum by Pierre Janssen, even though he always went by Jules, and Sir Norman Lockyer in 1868. If you look into the proceedings of chemical societies, you will discover that helium was discovered by Sir William Ramsay in 1895. And some articles will make a comment about helium being detected in the sun spectrum in 1868, though still attributing Ramsay with the discovery. Now, there's an obvious discrepancy. And when you look past that discrepancy, what you will quickly find is that the story of helium's discovery is really, really deeply convoluted. Okay, come on, next slide. Be nice. Okay, helium's cool stuff. It's one of the two elements that astronomers don't call metals. And about 24% of all the baryonic matter in the universe is helium. Here on Earth, it is rare, actually rarer than some of our atmospheric models can account for. Only about 5.2 parts per million. And almost every bit of helium we have comes from radioactive decay processes. Well, the wrong way. Yeah, the other forward. Unlike the other inert gases, helium's extracted from naturally occurring wells and usually associated with natural gas. The most obvious use is a safe lifting gas. So, the weather balloons you see here. But there are plenty of other applications, more than you could imagine, for the limited supply we've got. One of the major ones would be things like MRIs, where you need the liquid helium to keep the superconducting magnets superconducting. Perhaps room temperature superconductors will actually come out available. That might make a difference, but so far that doesn't seem to be the case. In any case, it doesn't stop us from frittering the stuff away with pretty party balloons that then blow up and fall down and make a big mess over the landscape. Now, when we were planning this meeting, Dave Chisholm, who is off discovering Europe, asked if we would have a helium voice. But since Dave is off exploring Europe, and if the older ones amongst us will recognize this guy, I will assure you that that was done with sound editing software and no helium was huffed in the making of this video. Now, a reasonable place to start in the story is just before the great solar eclipse of August 1868. And we'll need to look at the state of science in the mid-1800s, including what was then the emerging field of astrophysics. This is what the periodic table would have looked like by the opening of 1868, even though Mendeleev hadn't yet published his first periodic table. And that first periodic table didn't look anything like the one we're used to, but we'll use our version anyway. By 1868, chemists had isolated elements in almost every group of the periodic table, with one obvious exception. Perhaps it's not obvious simply because it's not there, and that's the group 18 over here, all the inert gases, all the noble gases. Spectroscopy had become a major field, largely because of the work of a fellow that most of us have heard of, Joseph von Fraunhofer, who published his first diagram of the dark lines. And here's a copy of it here, his hand-painted drawing, his hand-painted rendering of the dark lines. His final catalog would list the wavelengths of over 570 of these beasts, which was a pretty amazing accomplishment, considering that every single one of these had to be measured by hand with micrometers and plotted by hand. Fraunhofer is probably best known for these lines, but he was also a master glassmaker and instrument maker, and is usually credited with being the inventor of the modern spectroscope. And it's quite possible that his glassmaking probably killed him from inhaling gases of fumes of heavy metals. But we don't know for sure. Along with spectroscopy, though, instead of just looking at the dark lines, a number of people decided that they would start using the newly developed Bunsen burner to heat elements and heat substances, I should say, and see what bright lines were produced. And here we have a simulated emission spectrum of hydrogen. Gustav Kirchhoff and Robert Bunsen became probably the great pioneers of spectroscopy. It's not that fair to single somebody out, but these two really do deserve a high standing from it. And they were using Bunsen's then brand new invisible flame burner to vaporize samples of materials and see the bright lines. And what soon became obvious was that the position and character of these bright lines could be used to identify various substances. Now, we wouldn't understand how these lines would be produced until the 1920s, but long before that, spectroscopy had become empirically verified as a reliable analytical process. Now, here's a link that might not be quite so familiar to most of us. Léon Foucault, you know, the Foucault lens and the Foucault test, the same fellow. He demonstrated in 1849 that emission lines and absorption lines at identical wavelengths were produced by the same material. That's usually attributed to Kirchhoff, but this is actually the original work done by Foucault. And Kirchhoff then expanded that discovery to devise the laws of spectroscopy that he published in 1860. And this body of work, Foucault, Kirchhoff, Bunsen, would allow spectroscopists to compare laboratory references to absorption spectra. Around this time, Kirchhoff and Bunsen discovered cesium and rubidium, which you'd see over on the far left-hand side of the periodic table, entirely by identifying previously unknown spectral lines. And they'd identified samples of these incredibly reactive metals only because they already knew what they were looking for. Trying to isolate these things is not an easy thing to do, largely because the stuff is so incredibly reactive and it just tends to slag down into other compounds. Spectroscopy had become one of the more valuable techniques of the 19th century scientists, and instrument makers were taking advantage of the Industrial Revolution to, by that time long advanced, to produce marvelous instruments for discerning scientists who were willing to pay for their services. And astronomers, particularly the well-heeled amateur astronomers back then, were quick to use these new technologies, including the then new field of photographic equipment. For spectroscopy, the benefits were really, really obvious. Here is a copy of Henry Draper's first photograph of the spectra of the sun. And if you look carefully, you might notice that there's millimeter scales here drawn next to it. So everything would be put into this one photograph. And when you compare this to, for example, Bunsen's painting, I'm really tripping over names here. Fraunhofer's painting, you can really see how this became a massive improvement in spectroscopic technique. Eventually, these photographic plates would replace drawings and sketches, and you'd eliminate all this incredibly tedious and error-prone drawing and painting. It would take a little while. We weren't quite there by the mid-1800s, but the trend was obvious. Now, in addition to looking at stuff in laboratories, astronomers are also turning their spectroscopes to stars, and in the case of William Huggins, turning a spectroscope to nebulae. And in observing the Cat's Eye nebula, he noticed two green lines right around the 500 nanometer area that had never been seen before. So he suggested that since they hadn't been seen before, they must be an indicator of some unknown material, which he later called, and I'm never sure how to pronounce this, nebulium or whichever. It was never found on Earth, and its existence remained in dispute for decades. We'll see why it became even worse as the decades rolled on. I'll start my video. Fine, if you really insist. All right, here you go. I'm here. I was hoping I could hide through the whole thing, but at any rate, where was I? Oh yes, nebulium. The case wouldn't be closed until 1927 when Ira Bowen demonstrated that, in fact, what nebulium was doubly ionized oxygen, which we now know is O3. It's an old spectroscopy reference. The O3 refers to the number of electrons stripped. The one designation would be no electron stripped, neutral material. 2 would mean 1 electron stripped, 3 would mean 2 electron stripped, and so on. It's a little weird, but you do get used to it after a bit. Now, these lines here were originally considered forbidden lines. because they corresponded to electron transitions that by the early rules of quantum mechanics were thought to be impossible. But what they turned out to be was very low probability events. So low probability that in an earthly laboratory, you're simply not going to see them. You'd need an enormous volume of incredibly rarefied material, exactly like what you'd see in nebulas, to produce enough of these events that you could actually see them. So that puts nebulium to bed. I mean, it is an original substance in the sense that it's a new substance, in the sense that it was a form of oxygen that we couldn't see, but it certainly wasn't a new element. So now that we've got some of the preliminaries done, we can take a look at the solar eclipse of 1868, which made a huge swath and a very long eclipse, about 5 minutes in totality near the center, right across Southeast Asia and through India. And armed with the very latest equipment that instrument makers could manufacture, teams from everywhere, but particularly Britain and France, naturally, they had to go squabble about something, would set off to India and Southeast Asia to observe the event. There's some really interesting stuff regarding Siam in this, Thailand, but I had to chop that out. It was just getting a little too long, but look it up sometime. The great eclipse of the King of Siam. It's some interesting reading. So here are the two big names that we saw first in the description of who's supposed to have discovered helium. We have Jules Janssen, and yes, despite his name being Pierre, he went by Jules, and Sir Norman Lockyer. An interesting character, Lockyer. He became very, I don't know, almost proprietary about the sun, and the great physicist James Clerk Maxwell ended up putting together a little ditty about him, which ran, and Lockyer, oh, I'm sorry, I have to do it in a bad British accent to really make this work. And Lockyer gets cockier and cockier, for he thinks he's the owner of the solar corona. Yeah, I know it's a terrible accent, but it doesn't work without it. Now, one of the travelers going to British India was a French astronomer, because he was having some problems with the staff at the Paris Observatory, so he couldn't go with the French group to Siam. So off he went to British India. It was already known that during totality, you would have a tenuous but very bright region around the sun that would become visible at the moment of totality. And Janssen was keen to use his newest and greatest spectroscopes to observe that region. Lockyer remained back in England for several reasons. For one, he was recovering from an illness. It's never specified in the biographies, but who knows, could have been anything. And his own spectroscope had been delayed in delivery, something that we can all appreciate. The widget you ordered hasn't come in time for your trip. Anyway, that's what happened to Lockyer. So already we're beginning to see a problem here because Lockyer never observed the eclipse. We'll get to that in a minute. Already in England, we have this chap that you may remember from last month, describing when I was discussing stellar magnitude system. Norman Pogson, he was already in India, the director of the Madras Observatory, which is now modern day Chennai, and I'm probably killing the pronunciation, but by that time he was a disgruntled civil servant. He was out of favor with his superiors, largely because he continuously grumbled about his finances and lack of support. They really didn't know what to do with him, but he got along very well with the people at the observatory and with the regional governors in India, so they really couldn't sack him. So they left him there, but kind of off to one side. And even though he was much less well equipped than the expedition teams leaving England to go to India, he was determined he was going to do his own examination of this eclipse, including his own spectroscopic studies. And of course, there were many, many more teams. One of them being an English team led by then Major James Francis Tennant, who had just come back from putting down the Sepoy Mutiny. Anyway, there's all kinds of stuff here that can keep you going for ages, and I won't because I can't. Now, these are not the first pictures of a solar eclipse, but they are certainly one of the earliest ones. And these were done both at the moment of totality and just about a second after totality by Tennant's team. This is done from the Indian town of Guntur, in right practically in the center of the band of totality. Tennant describes pulling off his dark glasses right after totality began, and he writes, "My attention was caught by a tall, narrow, brilliantly lighted, rose-colored, horn-like protuberance, which has to go blast. Sorry about that. Has to be this one. I can't think of what else it could be." And then right after totality, you can see here how it's just not quite as bright, but it's still quite visible. Across town, by sheer fluke, because they had Tennant and Janssen hadn't communicated in advance, Tennyson, good Lord, I'm thinking of the light brigade here. Janssen was aiming the slit of his own spectroscope just off the sun's limb. Where exactly, we're not sure, because that I couldn't find that in the records. Perhaps it was here, or perhaps it was down here. I'm really not certain. Excuse me. Oh dear, excuse me. And at the moment of totality, he watched the dark lines become replaced with bright lines, an emission spectrum produced, as he thought, excuse me, by the protuberance, which we'd now call a prominence. Now, it'd be a couple of years before astronomer Charles Young would record a flash spectrum, but we can still use the flash spectrum that I gave you a sneak preview of to get a sense of what these astronomers would have been seeing for the very first time, because nobody before this had seen a bright light spectrum from the sun. If we look here, you may recall this one from earlier this year. It's a beautiful flash spectrum. Looking along here, the curves are because of the shape of the sun, because we're actually getting a spectrum right from the limb. So these curves correspond to emission lines, and we can see them right along here, along this line. This is just a repeated version down on the bottom. So the curves are lines just because of the shape of the sun. And we can see where the major lines are. So what they would have seen would be like small vertical lines somewhere around, somewhere around here at this point, just above the white streak. Now, if we take a look moving along here, we can see that there's kind of a yellowy, ragged line here. And here's my question for you. Is this a single spectral line? Is this multiple spectral lines? What is it exactly? And it's not that easy to see. It's not that easy to be sure. We have the advantage in that we've seen plenty of these, and we know how to interpret it. But you have to remember that every spectroscopic observer from the 1868 eclipse reported having difficulty seeing the bright line spectra. And they also didn't have the equipment that we could use now. And even more to the point, they weren't used to looking for these lines. The bright line spectra was stuff that was done in laboratories by chemists. A few astronomers, the early astrophysicists, we call them now, had reference setups in their observatories, but very, very few of them. I think Huggins was probably one of the very few who did it. So this was all very, very new stuff. You have to also remember too that what we assume, we take for granted that everything we're seeing is pretty linear, and that is just not the case. So let's put a chart of Fraunhofer lines up next to this. I've chopped it off just to the red side of the C line, which we would know better as the hydrogen alpha line. And here we can get a bit of a hint. So down here we've got the G line and the hydrogen beta line. And here we have the D line. Now these letters here, these are the ones that Fraunhofer used. And these are simply alphabetical lines. He just went from the red side and lettered them to the right side, to the blue side. And as he saw finer and finer lines, he went back over it and reused them with lowercase letters. But they really didn't have any meaning. But very quickly, people began to use the names to indicate the line. So here we have the D line, which eventually the resolution became good enough that you could see that it was actually a doublet. It was actually two lines. And well, we're not quite seeing that here. But were we? Don't forget, this is all equipment that our stuff, even the cheap stuff that you can go and you can buy and order and stick in your camera, will probably do a better job than what they had available then. Now, here's the interesting part. The observing reports make it clear that most of the observers, and most is the key word here, including Janssen, reported the bright yellow line as corresponding to the sodium D line. In other words, this dark line here, they reported, okay, it's the sodium D line. I shouldn't say, they didn't say sodium D line, my mistake. They referred to it as the D line. And they simply took for granted, this is the D line. Hang on to that thought. Now, about 100 kilometers away in the town of Masulipatam, which is also known as Machilipatnam or Bandar, and I'm not sure why, Norman Pogson's team was busily recording and observing the eclipse. And this hand-painted diagram shows the records that Pogson made. Here are the bright lines that he measured, and he put them against a standard dark line spectrum. And I'll give you a close-up here of the region around the D line, and you'll notice that they don't precisely line up. Pogson writes specifically that this bright line, quote, must have been either coincident with or very near the place of the sodium line D. In other words, Pogson wasn't sure what he was seeing. All the other observers simply, oh, it's the D line. It's the bright version of the D line. And don't forget too, I mean, they would have seen sodium D lines, as these were very popular. The bright sodium lines were very popular exhibits in science meetings and such like back then, because they're very easy to make. You simply sprinkle table salt on a Bunsen burner and get the sodium D line. It's very fleeting and evanescent, but you can make it work. So Pogson, of all people, is not certain of what he's seeing. And there's a good reason for that, because even though he didn't know it, he was actually seeing a bright line of helium buried into that D line, because don't forget the resolution wasn't that good. You couldn't split this into multiple lines very easily. Now, we've got a big advantage over the fellows in 1868. Yes, I'm sorry, they were all fellows. We get to flip ahead to the answer section. So I've added a synthetic spectrum. You may remember this one. And here we can see the hydrogen lines, the sodium lines, a doublet if you look carefully, and this helium line right next to it. And here we have it. Here's the trick. This little thin ragged bit is the sodium doublet, and here is the intensely bright helium D3 line. So let's compare these emission lines, though, to the absorption lines, because this diagram doesn't show you the whole story. Here's where it gets, at least to my mind, incredibly fascinating. Take a look at this one. Here again, simulated spectra. And I've looked at just the major ones that are easy to see in flash spectra. So here we've got the calcium K and the hydrogen lines, magnesium triplet, which actually does show up quite nicely as a triplet. You could see a sodium line, the sodium line here. If you look carefully, it's actually a doublet. The black line down here, if you look carefully, that's a doublet. You see a triplet here for magnesium. But take a look under the N here in sodium, and there is no black line here. And that's not simply because I haven't drawn it in. You won't find a black line there in Fraunhofer's diagrams, and you won't find a black line there in modern solar diagrams. It's not there. Here we have a bright line that has no correspondence at all to an emission line, to an absorption line. It's hardly wondrous that in the limited capabilities of the spectroscopes, they'd see just the one line here and only eventually would be able to split it into three. What's happened here, again, we get to flip ahead to the answer section. The sun is too cool to produce helium lines. You've got to wait until you get up to class B, class O stars before you get stars hot enough to produce helium absorption lines. But if you recall from earlier this year, the spectrosphere, man, oh man, I'm tongue-tangled today. The chromosphere gets hotter and hotter as you go up from the surface of the sun, the effective surface of the sun. And by the time you get up to around 1800 kilometers or so, it's hot enough to produce the brightest emission lines of helium. So we're seeing here a chromosphere feature that doesn't match a photosphere's feature. And of course, now we can understand it. Back then, there was no way that anyone could. And remember the state of the periodic table. Nobody found anything in what we now know today to be group 18, depending on how you refer to the periodic table. Nobody'd seen these before, and nobody had any real idea of just how big the periodic table was going to get. So now we get back to Janssen and Lockyer. You might reasonably wonder where these people fit into this story, and where Lockyer in particular fit into the story, because he was back in England recovering from his illness and waiting for his spectroscope. The telegrams were coming back from India, just pouring back from India over the early telegraph lines, and reporting that bright lines have been found in prominences beyond the limb of the sun. Somehow, though, Lockyer seems to have gotten Janssen's report mixed up with Pogson's report, and believed for many years that Janssen reported a bright yellow line that was a bit offset from where the D line ought to be. And as I mentioned, he wouldn't discover that error for years. So let's look at what happened after the eclipse, because that's when the story starts to get even more interesting. Most of the observers packed up their equipment and went home. Janssen, though, he stayed behind with all his gear. And he figured if he just aimed his spectroscope slit where he knew he'd find a prominence, because he recorded it all the day before, that maybe he'd be able to see the bright lines that he'd seen before. And the method worked much, much better than he'd ever hoped. And he wrote in a letter to his wife, "They sent me to discover an eclipse for 5 minutes, and I am bringing back to them the perpetual eclipse of India." Lovely poetic term, that one. He brought back a perpetual eclipse. Don't worry, I'm getting to Lockyer. Now, Lockyer's new spectroscope arrived in October of 1868. Janssen was still on his way back to France. Now, it's not clear why Lockyer tried what he'd earlier called fishing off the limb of the sun to look for prominences, or in exactly where to look, but perhaps the telegrams were explicit enough that he was able to look. And he successfully got a bright emission spectrum. His notes include a comment about a bright yellow line near D. Another thing to remember. So he sent a note about his technique to a colleague at the French Academy of Science, and in one of the marvelous flukes of the tale, Janssen's letter describing his success with fishing off the limb of the sun had arrived. The history is not entirely clear. Some accounts say the same day, but at the very least, they arrived right next to each other. And they were both read at the same French Academy of Science meeting. And the Academy later decided that Lockyer and Janssen had jointly discovered a new method for observing solar prominences. A few years later, 1872, the French Ministry of Public Instruction had this medal struck to commemorate this discovery. Now, you will read accounts in decent periodicals and decent references that tell you that this was struck to commemorate the discovery of helium. It wasn't. It was struck to commemorate a method of analyzing the sun. And even if you've got terrible French, you can read the lettering right here around the medal, Analyse des protuberances solaires. Okay, my French is horrible, but you can figure that one out too. So that's what this medal was for. It wasn't for discovering helium. It was coming up with a new way to study the sun, the perpetual eclipse that Janssen described. And Janssen and Lockyer, unlike the typical patterns of the day, which were terribly antagonistic, they just decided, yeah, we both did it, cool. And they patted each other on the back and took joint credit for it. And I'm not sure that they were ever good friends, but they remain on good terms for the rest of their lives. Now, Lockyer still continued fishing around for prominences. And towards the end of 1868, he became quite clear that, in fact, you were seeing 3 lines here near the D region. And he began referring to a new D line, which eventually would be called the D3 line. Nobody knew how to make it. Lockyer's notes make it clear, in fact, that he thought he was dealing with some kind of hydrogen. Again, don't forget, nobody really understood elements at this point. Not the same way we do today. They certainly didn't understand where the lines came from. So here we've got the sodium D1, D2 lines, and here we have the helium D3 line. Now, if the numbering gets a little weird, don't forget that Fraunhofer's original lettering went from red to blue. So the numbers are going to increase from red to blue as well. And before 1868 was out, Lockyer would discover that, in fact, the solar prominences were not the only source of emission lines. He described an envelope surrounding the sun on all sides, which he and some folks at the Royal Society decided should be called the chromosphere because of the bright colors of the emission lines. Interestingly enough, not because of the pink color. It was, according to the references that I read, because of the brightness of the emission lines. Doesn't really matter, I suppose. So this is when the term chromosphere was created. This probably fed into the mythology around the discovery of helium. So what happened to these folks? I mean, this is pretty much the end of the astronomical tale. Janssen went on to be his classic peripatetic self, wandering all over the earth, to the great discomfiture of his wife, who once wrote that other wives have to deal with mistresses. I have to deal with your journeys. I'm not sure if she, anyway, never mind. This monstrous thing here is Janssen's photographic revolver, and you can see the photo plates here. This was an incredible method of getting multiple images that would actually later be used for the earliest motion pictures. And in this picture, he's en route to observing the 1874 transit of Venus from Nagasaki. Lockyer went on to become the first editor of Nature magazine, which is the same one that we still can get today. Pogson, well, I didn't show the picture of Pogson here. Anyway, he went on to become the master of the mint in Calcutta, a modern day Kolkata. They'd all seen the signature of helium on the sun, and up to this point, none of them had made any claim whatsoever of finding it. And this is a key thing to remember. They had no idea what they'd found. Lockyer and Pogson had some indication that there was something new. If Janssen did, he didn't write about it. So I find this kind of interesting. I mean, they'd seen it, but they didn't know about it yet. Now, why not? I mean, we had Huggins with nebulium. And then in 1869, the astronomers Charles Young and William Harkness independently discovered a new line in the eclipse of 1869, a new green chromospheric line around 530 nanometers, never observed on Earth. And since it was in the chromosphere, don't forget the terminology was still varied. The corona was still that wispy bright ring around the sun that you saw in an eclipse, so it became known as coronium. There are some other names tossed around as well. Again, we didn't discover what this was until about the 1930s, when Grotrian, name you might remember from spectroscopy if you're interested, and Ed Lynn discovered that this in fact was produced by iron 14. In other words, iron with 13 electrons stripped off. And how could that happen? I mean, it would take millions of degrees. Well, as we all know now, the corona is millions of degrees, and it was quite hot enough to produce this line of weird iron, which again, you could not see on Earth. Again, it's a unique thing, element of, an aspect of stars, but not something we could see down here. So this was beginning to get a little difficult for people, because everybody and his dog was coming out with, oh, I've got a new element. There's all kinds of them. There's jargonium, there was nobelium, there is newtonium, there is oranium, orionium. I mean, you name it, somebody was coming out with it. This whole idea of elements that we could find in a spectrum but couldn't find on Earth, this was becoming to be, UFO observing territory. I mean, this is crackpot stuff. Nobody really wanted to deal with it. And With all this, though, Lockyer still kept investigating in the D3 element, as he called it. Now, even before the eclipse, he'd started working with Edward Franklin because he wanted to have a chemist in England because he wanted to have a better understanding of how hydrogen lines could relate to the actual circumstances. And Franklin and Lockyer experimented with hydrogen under a whole bunch of temperatures and pressures and discovered that, in fact, the spectrum would change under different physical conditions. And they used this to establish that the gas in the chromosphere had to be at a pressure much lower than Earth's standard atmospheric pressure. Now, Lockyer had once thought the D3 line was associated with hydrogen, and he would again come to think that, but he was beginning to suspect that it was possibly an unknown element. And Franklin, because of the crackpots with all kinds of weird elements that never panned out, just, no, don't do it. Didn't matter. Lockyer started referring to D3 as helium, after the Greek deity of the sun, the Greek word for the sun. But he didn't use this in public. It started to leak out into the scientific community, but he didn't actually use the term. The first guy to use the term was this chap, Lord Kelvin, in an address to the British Association for the Advancement of Science, which I'm not sure. Apparently, Lockyer was not keen on that, and Franklin was apparently just aghast because he didn't want to have anything to do with a new element. So there ends the story of helium for a little while. So we're going to move ahead to 1894. We've got a few more blocks filled in, and we have the first noble gas, argon, which was actually named after the Greek word for lazy because it wouldn't react with anything. Ramsay was involved in discovering argon, and he would later go on to fill almost the entire column. And in fact, that's what got him his Nobel Prize for Chemistry in 1904. Now, in 1895, this dapper gentleman, William Ramsay, isolated a gas from a mineral called clevite, which was actually a low-grade version of this gorgeous stone here, uraninite. And what was happening is when he dissolved this stuff, it would produce, well, we already know the answer. What do you get out of uranium? You get alpha particles, which are what? Helium nuclei. Once he isolated this gas, he busily took it off, heated it up, got a spectrum, and discovered a brilliant yellow line smack dab at the D3 line point. And in his report to the Royal Society in April of 1895, he reports that this was the material that Lockyer had been speculating about for years. And he goes on to write, Mr. Lockyer many years ago gave it the name helium from its occurrence in the spectrum of the sun's chromosphere. In yet another twist on the story of helium, at almost the same time, almost to the day, a pair of Swedish chemists named Per Theodor Cleve, the same fellow who discovered clevite, and Abraham Langlet also isolated a gas emitted by clevite, also put it in the spectroscope, and also discovered a brilliant yellow line around the D3 line. And in their report to the Royal Swedish Academy of Science, stated that the gas at least contained helium. But oddly enough, they never mentioned helium again. It never showed up in any of their papers. It never showed up in any of their discussions. One report says they withdrew their claim, and I don't know if that's the case, but they certainly never talked about it again. And Ramsay became established as at least the discoverer of terrestrial helium. And even Ramsay, in his address for the 1904 Nobel Prize, again made reference to Janssen and Lockyer. Lockyer, however, had gone on to write that the D3 line in his book, The Chemistry of the Sun, went on to write the D3 line was, quote, probably a fine form of hydrogen. So he seems to have gone right back on it. After 1895, everybody started talking about helium, and somehow that myth became developed. So here you've got the situation. You have helium producing a nice, brilliant lemony color of light that gets split into this nice spectrum, except in the sun, you're not going to see much more than this. You can get it from uraninite. You can see it in the sun. Who discovered it first? Who knows? I think it's best to say that probably everybody discovered it, but didn't quite know what they tripped over it because they didn't know what to look for. It was only when people like Ramsay, and I've cut this off because I'm already running way over time, discovered that, you know, things just aren't adding up. So I think the thing to take away from this one is you can't package discoveries in a neat, tidy story. Even this story that I've presented to you, and you know, wake up now because I'm done. You can proceed with safety. Even this is overly simplified. There's an entire book on this topic. So do yourself a big favor. See a neatly packaged story, forget about it. Go take a dig because you're going to discover something really, really cool. Like this. Or at least I think it's cool. Maybe I'm just a geek. Anyway, I hope you've enjoyed this and haven't had too much of an urge to throw fruit at the screen. That's it. Good night. Enjoy. And Dave's not here, dude.
All right. Thank you, Tim. All right. Up next, we're going to have a presentation on solar observing by Andrea. Oh, I was muted talking to myself. That's great. All right. Next, thank you, Tim, for that presentation. I'm sure we all learned a lot about helium and its history.
Oh, trust me. I mean, you can dig into this. Andrea asked the name of the book. I'll post that on the talk. It's a cool book. Anyway, if you read it, you're in serious danger, like I was. Okay.
So
bye,
we
everybody.
have one question. We have one question from Mick. To what degree did this lead to interpretations of quantum mechanics?
Boy, there's a question for you. I'm not sure it led to interpretations of quantum mechanics, though it was certainly tied up in it. Part of the problem with quantum mechanics was to try to understand electron transitions and allow in what would be allowed states. So they were all quite intertwined. One of the first quantum mechanical jobs was to provide a reasonable model of the Balmer lines, actually not even the Balmer lines, all the lines in hydrogen. And Niels Bohr actually advanced on the Bohr model that we had to learn in high school to put together that framework. So did it lead to it exactly? Possibly not, but it was all tied in together. Quantum mechanics allowed us to understand the line formation process.
Cool. All right. Thank you, Tim. Any other questions, anyone? Going once, twice. Nope. All right. You're off the hook now,
Sold to
Tim.
the man with the earphones.
All right. All right. And for the third time, I'll try this again. All right. Now we move on to a presentation on solar observing by Andrea.
Hi, my name is Andrea Girones, and this presentation is going to be about the equipment I'm using for solar observing, some of the features on the sun that we can observe from Earth, as well as some of the interesting activity that's been going on the sun over the last few months. I am recording this because last time I was supposed to give this presentation, I came down with laryngitis. So better safe than sorry. I have recorded this and I don't think you'll be seeing my face for the rest of the presentation. Many of you know I began my solar imaging with a small and portable Lunt 40 telescope. I think it gives me great images, and it's certainly a reasonably priced way to begin taking H-alpha imaging. This is an example of one of the images that I took with the Lunt 40 millimeter H-alpha scope. I normally image in monochrome and then I add false color in Photoshop, and it is clearly a very capable imaging solar scope. Solar activity is increasing in 2023, and there are more and more storms, sunspots, and solar flares. I rely on these three sources of information. The Space Weather Live, there's an app and a website, as well as the Gong website, which provides live H-alpha views. It's really good to go and see what's happening on the sun. And Space Weather Woman, Dr. Tamitha Skov, is a solar physicist, and she has a YouTube channel where she is updating you on the current CME, solar flare, etc. I do a set of images on my phone, snapshot of the space weather region map, and then also take a snapshot of alpha images long and so the network has H-alpha telescopes across the world, so you can open like an up-minute look at what's happening in the sun, look and see anything interesting, if there's filament, and it's a way of out what's happening in the sun, but sort of track of. I like to merge two bits of information because, as you can see, the sun is so active, it's hard to track.
Chris, can you pause the video for a second? We're getting some audio issues, I think. Maybe we can pause it and start it again and hit play and see if it improves.
Regions. The third source of information that I mentioned was Dr. Tamitha Scott's YouTube channel. She does a lot. She does a weekly update on solar.
We're still getting the choppiness. Let me put Andrea on the spot and ask if she can speak to this video, and I'll turn off the audio.
I could actually probably play it, but all right, I will speak to it.
Bear with me while I first turn off the sound and figure out how to do that.
There should be a mute button. Oh, now I gotta have notes.
Okay, tell me when you're ready and I'll play the video without audio.
All right, don't play yet. So these are basically two different apps on my phone that I use whenever I'm doing solar imaging. The Space Weather Live app will give us all of the sunspots. And as you can see from the slide, I think it's from sometime in July, there were millions and millions of sunspots. The Gong network, and I'm going to post the link, is a really great place to go and look at the sun and H-alpha. They have telescopes set up all around the world, and they're really up to date. So before I go out imaging, I take a look at the Gong network to see what is actually happening and where I want to take my telescope to. Keep going. I guess we can go now. If you want to play the video, Chris.
It is playing.
Okay, so it's waiting for me. So while we're talking, so I decided to try a new imaging setup. It's a quark chromosphere solar filter. And I did buy a Starfield Optics 102 millimeter refractor, which I use with the ASI 174 millimeter camera that I already owned. And the goal here was to get a bit of a deeper, more, I can hear my husband's lawnmower coming along. The idea here was to get a better, deeper, high resolution pictures. Here you'll see I have an H-alpha set up on one side, and you'll see the white light set up on the other. In the early days, I used a diagonal, and you can use a diagonal because you could also use it for visual imaging, visual observing. Eventually, I got rid of the diagonal, and I'll talk about that. And you can see in the white light version, I actually made a handmade Bader solar.
Andrea, we've lost your audio now.
My audio, okay.
Now you're back.
I'm back. I won't move. All right, so this is my imaging train now. I have a UV IR cut filter at the front. You need that as a energy rejection filter. If you have a bigger scope than 102 millimeters, you actually will need an external ERF filter at the very front. And now the little pointer is looking at the quark itself. There's a tuning knob, and it does require AC power. This is a reducer. And the reason you might want a reducer with a quark is the quark actually has a built-in Barlow, a 4 times Barlow, which is incredibly zoomed in. So the reducer helps get a wider field of view. I also use an ADC, which is an atmospheric dispersion corrector, and I use it actually as a tilt adapter. When you are doing solar imaging with a Barlow, you can get Newton's rings, and they're really hard to get rid of unless you're able to tilt your sensor. And so I use an ADC. You can use a normal tilt adapter. I think Tony has a tilt adapter that he uses. And so what I have here is also a straight through imaging train because with the diagonal, I was getting a lot of wobble. And wobble was not good because you actually have to take flat frames with solar imaging. And if you have a wobble in your imaging train, then you lose your flats. This is what you will see with a basic white light filter. You can actually see an awful lot, especially right now because the sun is so active. There are giant sunspot regions, and you can, along the edges, you can see the faculae. And I strongly encourage anybody to just make a homemade white filter and see what you can see with your telescope. With the 102 refractor, I can get a full disc with a white light filter. This is my current imaging train. As you can see, it is straight through, but you do need a lot of back focus. So I have an awful lot of adapters. It gets quite long. And that big black thing at the end, I'll explain what that is later. But I found a way to make a double stack using the Etalon from my 40 millimeter scope. And I'll talk a bit about double stacking in a bit, and that will tell us, I'll explain what that means. But I like the straight through imaging train better, although it's quite long and I have a cushion underneath in case things fall out, because I wouldn't want that to happen. Yeah, I'm circling now the Lund Etalon. That's a shame the video didn't work. Okay, I'm waiting for the next slide now. Nothing is happening.
No, the video is playing and you just have to wait for it to advance to the next screen there.
All right, so this is an image that I took with the reducer, and it's a 0.5 reducer. And I'm going to show you a couple of different fields of view. And this was quite a lovely sunspot region. I couldn't tell you what date I took it because I don't have my notes anymore, but I believe it was sometime in June. And as you can see, it's quite a close-up view, and this is with the reducer. But keep an eye on that little sunspot region because we're going to do a close-up look shortly. But you can clearly see the dark umbra and the lighter penumbra, and you can see these fibrils that are connecting along the magnetic loops of the sunspot region. And here is a close-up look. So this is what you see with the reducer and with no reducer. So it's extremely zoomed in. And while it's very nice to get a lot of a close-up look at the sunspot, it's sometimes hard to get a full disc or to try to do a mosaic. So that's why I like to work with the reducer. What you can see, much more close-up detail, it's high resolution. And now this is another image. It's not the same spot, it's a different spot, but it's an image I took with a double stack. And as you can see, it's a slightly different image. You're seeing a much narrower bandwidth. And that's why a lot of solar imagers do a double stack if they can. It helps them get greater contrast for the features. We are doing a narrower field of view, and they're a little different level in the chromosphere. I haven't quite sorted out exactly my method with the double stack, but I think it is promising. And I have a few other images with the double stack. Aha, okay. So one of the things I did to learn all about the sun is I undertook the Astronomical League H Alpha certificate program. And it's a program where you have to identify a variety of features on the sun. And it really sort of helped me learn about the sun and identify features. You could do the certificate either by doing sketching, and they actually have really nice templates that you can use for solar sketching, or you can do it by imaging. Filaments are one of the features you must identify for the H-alpha certificate. A filament in this image is the big S, the dark S that you can see. The filaments are basically solar storms that are in the chromosphere, and they're sort of high above the surface of the sun, or the photosphere. And in this image is non-inverted, so they look dark against the surface. You also have to identify prominences for the certificate, and not just one prominence. They want you to identify 10 different kinds. There are hedgerows, there are pyramids, there are arches, there are half arches. And so that was a really fun part of the H-alpha certificate. A prominence is just a filament that has hit the edge of the sun. So once again, you're seeing a solar storm that looks dark against the surface of the sun, which is bright, but looks bright against the darkness of the sky. Sometimes you'll see a filament that partially reaches the edge, and it's called a filaprom because it's half filament and half prominence. Spicules are basically a chromospheric fringe that you see along the edge. And here you can see along the edge of the sun, there is a sort of pale little fringe. And these are little baby filaments that pop up and down about the size of the Earth. They're short-lived. Along the surface of the sun, they look more like little hedges or little bushes. This is another feature you must identify. They're called plages. Plages, of course, is a French word for beach. And these are the very bright regions that you see around a sunspot. They look like a bright, pretty beach. And then fibrils are basically a chromospheric structures that follow the magnetic field lines that connect two different sunspots. So there's sunspots almost always come in pairs, and that the fibrils are these dark, I'm pointing them out, little dark regions that connect, that travel, material that travels along the magnetic field. So you need to identify that feature. Another feature is an emerging flux region. And this is not a great picture, but it was the one I used for my certificate. And that's pretty much exactly what it says. These are the flux ropes that are just starting to pop through the surface of the sun through convection. And eventually they will form sort of two footprints, which will become sunspots. So it doesn't look like much now, but eventually this will become a sunspot region. Later on in this presentation, I have a time lapse, which will show some emerging flux regions, and it'll be quite neat to see them sort of before they become sunspots. The next feature is something called Ellerman bombs. And frankly, I'm going to be honest, I've never quite figured out what Ellerman bombs are. I have tried to research them. If there's anybody out there who knows what they are, I'd love to hear from you. The way it's described is these are supposed to be little micro flares, so little bright spots around a sunspot. I managed to sort of identify them by looking at a couple of time lapses. What I have in this image are some very bright little spots around the sunspots. I don't know if those are Ellerman bombs, but that is how they are described. So once again, that's another one of the features that you need to identify. Now I thought I would cover some interesting things that happened on the sun in May, June, and July. This image actually is one of the images I took with a double stack, and I have inverted the imagery. So the dark filaments now look white against a darker sun. And we often do inverted images for the chromosphere because they look pretty. This is what happened in May. There was a reverse polarity sunspot. So normally there's a pattern. All these sunspots in the northern hemisphere follow the same pattern. Either it could be a positive spot leading a negative, and the opposite occurs in the southern hemisphere. But this little sunspot came along and it was backwards, and it was next to AR 3293, and that caused a very unstable magnetic situation. And so this sunspot region 3296 sent off flare after flare after flare the entire time it crisscrossed the face of the sun. And at some point we thought it might launch the CME and create aurora, but it never did. And this is some of the information you can get on Space Weather Live. You can, for every sunspot region, you can get the sort of magnetic mapping. Oh, it's gone. Oh, it's gone back to the beginning now, Chris. That's not good. Ah, yep, there we go. No, one more. Yes. So as you can see here, there's a red region followed by a blue region. And normally in the Northern Hemisphere, you will see it's always a blue region being followed by a red region. And this was reversed, and that's how you can go on to Space Weather Live and get interesting information. The more intertwined your red and your blue are in a sunspot region, the more magnetic activity, the more flares will likely occur from that active region.
Sorry, you got to hold on, Andrea, while I fight with the dual audio.
Oh, I'm sorry. I thought this would be helpful, but it turned out not to be. So I apologize to everybody. It worked for Tony. I don't know. He has a secret way of doing this.
Now you can go ahead.
All right, another big feature of the last couple of months have been some very large filament launches. The filament launches essentially, as you recall, is a solar storm. And when they erupt from the surface of the Earth, it basically sends large amounts of solar material. All right, keep an eye at the very top of this video, and you will see a filament launch from the polar filament. There it goes. Essentially, that is one of the many solar filaments that have been launched in the last little while. This image is from a program called J-HelioViewer. And this is the sun, I think it's SDO in 304 angstroms. Moving pretty slow, but you can see all the bright active regions. You can see the polar filament launching, and you can actually see some other areas that are getting material launched. So this is the same date, and you'll see all the material that's being launched. This is the LASCO viewer, and did you see that was a huge, beautiful filament that was launched on June 12th. As you watch this, though, you'll notice that that wasn't the only filament that was launched, the only material. One of the things that is happening is people are noticing that the number of CMEs that are occurring every day is increasing, and solar physicists are taking note of this. Now, hopefully this is going to move to the next. Yes, there was an X-class flare as well, June 20th, and it was just rotating over the southeast limb, and it was from active region 3341. And I believe it was one of two flares, X-class flares we had in June. And as much as everybody is excited by X-class flares and that they're very dramatic, they could, if they were in the Earth strike zone, they could cause a lot of damage on Earth. And the Earth strike zone is the area which is sort of the western edge of the sun. Now look towards the east, southwest, and you will see that was it. That was the X-class flare that it launched a massive, huge amount of material. But it certainly wasn't the only thing happening that day, as you can tell. There was simply all kinds of material being launched from the sun, none of which produced aurora, I don't believe, from this day, or maybe it did, I don't recall. Because we're seeing so much activity from the sun, some of the solar scientists believe we might be a lot closer to solar maximum than we thought. Now, this presentation was originally supposed to follow Tony's presentation. You'll recall he took an image, I think it was June 20th, and this was the next day. And that very vertical prominence that you see on the sun, he didn't really know what it was because he couldn't quite see it all. I took this time lapse the next day, and you can actually see that the little tiny thin prominence is connected in some way to the larger prominence. This was an area coming around the northeast limb. So this was an active area that was just starting to come around the corner. Another feature of the last few months has been some really, really large sunspot groupings. One of the very first ones was sunspot area 3354. And it was just a humongously giant, I can't express, my adjectives are a bit much, but it looks really big in H alpha, but you should see it in white light. It was one of the biggest groupings we have seen so far. So after taking this time lapse of this sunspot group, the next day I went out and tried to take an image of it in white light. And you'll see here that there wasn't much else happening on the sun, but this was quite an enormous area. There was a lot of cloud, and I couldn't actually get a stacked image because of the clouds, but here I just included the video, and I think you get a feel for just how massive the sunspot area was. There have been, since this time, there have been other really large sunspot areas. And again, there was getting more and more of them. That's another sign that we're approaching solar maximum. And the next day, I did get a white light image of 3354, and it had started to already move out of the way. Now, this is the last update because I was given another month. So I am going to talk about a couple of things that happened on July 28th. No, this is July 28th. Okay, never mind. I think there's another one coming. Now look at the big S in the middle of the sun and just keep an eye on that one. And you can see, hopefully you can see a big filament launch. That was almost, and then there was another sort of bunch of flares along the west edge. That was a big launch that was sent towards Earth. They were hoping that it would cause aurora. Eventually, it didn't really turn into much. And we're going to see it here on LASCO. And you'll see just how much material went out just on that one day. And hopefully it'll start going now. Oh, it's not moving. Oh, there it goes. And you can see a big launch for the southwest. Oh, and the big one off to the side. And then the filament will go. Oh, that was a pretty one. Just so you know what you're seeing right now, the speckles on the screen, that was a radiation storm that was launched by the sun on that day as well. This was an image that so this is a time lapse that I took. And a couple of big sunspot regions. I was trying to take an image of a filament because there have been so many filament launches. You'll see the big sunspot AR3387, but right beside it, that dark gurgly area, that is an emerging flux region. And there's another one coming into view now. And those two areas became designated sunspots a couple of days later. So while the filament, I was trying to do a picture of the filament, I didn't get any eruptions of filaments on that day. All right, and finally, this is my final just update because July 3rd, 31st, August 1st, and August 2nd, there was a big, 3 different storms were launched, one after the other. And I went to Helioviewer and I tried to see if I could capture them on this image. And you can sort of see some material launching, but it wasn't really clear. But the bottom line is on these 3 days, 3 solar storms were launched in the Earth strike zone, one after the other after the other. And as they hit the Earth, they built on each other and they built on each other. And on August 4th, we had aurora. And this was what the aurora looked like. And you'll be happy you don't have sound because I have very dramatic music here. But this was the video that caught the news cycle. And the reason I have so much pink is because I did use my Astro modified camera. So here it is, and I have my Facebook, I think, has a little sharper version, but that's why this is a, sort of shows the link between the solar storms and the aurora. And that's my presentation.
Great, thank you so much, Andrea, and we apologize for the technical difficulties we were having there. But nonetheless, it was a very fascinating presentation. All right, and I think, is this the right slide, Chris?
Yes.
Okay, so we've got some open positions in the club. We're looking for a meeting chair. Currently, Dave Chisholm is covering that role in the interim, and I'm filling in for him today. As Tim said, he was exploring Europe. We're also looking for a national representative to attend the national center, the national meetings on behalf of the Ottawa Center. And we're also looking for a hospitality coordinator for our in-person meetings. So if anyone's interested, feel free to reach out to any one of us on council. Next slide. All right, so we are going to take our break. We'll keep it short since the meeting is running pretty long, maybe 5 minutes. And the trivia challenge for this month is, which star is Alpha Ursa Minoris? Okay, so we're going to jump right into it. Up next, we've got Rig Wagner, who is our resident astrophotometrist, to give us a presentation on photometry and light curve analysis. Rick, take it away.
Thanks a lot, Oscar. So I wanted to talk a little bit more about a star I was observing earlier, V3124 Cygni. This is a high amplitude delta Scuti star. These are stars that are on or near the main sequence. They're generally about twice the mass of the sun, and so somewhat brighter. They pulsate by what's called the kappa mechanism. If you recall Tim's discussion about helium ionization, that takes place at about 40,000 Kelvin. And that's in the case of stars like the Delta Scuti stars, that takes place beneath the surface. And as the helium ionizes and deionizes, it becomes more and less opaque, and that basically creates a valve on an engine that causes the star to pulsate. So this star varies from about 10.3 to 10.6 magnitude with a period of about 2.5 hours. I took 3,700 images of it on 19 nights.
Sorry, Rick, I'm just going to pause you for a second. Chris, were we supposed to let Rick share his slides? Was he
No,
still seeing the...
I'm waiting for Rick's prompts to advance slides.
Gotcha, okay.
Okay. So let's go to the first slide. We have a picture of the star. It's the brightest one in the very center of the picture. So 3,700 images, 19 nights over a period of about 3 months. So using a program called AstroImage-J, I measured the brightness of the star on all of these images in comparison to a group of unvarying stars in the field of view. So then what I get is basically a light curve, a measure of its brightness as a period of, as a function of time. So next slide. You can see this is the data from one night, several hours. Nice light curve. One of the nice things about these fast variables, you can see I've got a whole over one period, over 2.5 hours. So I've got the whole period of the star. So then a few nights later on the next slide, I also get more than one period, but I also get a light curve that looks dramatically different than the last one. And the fact that they changed so much is suggestive that the star is actually probably pulsating in more than one frequency at the same time. Next slide. So if you look here, this is all the data phased into a single cycle. And you can see that each night's data is kind of braided through this thick rope of blue dots. So what's going on here? I wanted to analyze the data and see what does this mean? What's going on? So I talked about, let's go to the next slide. So I talked about this star back in February briefly, but there's been some new developments. And I've also found a new tool for analyzing this kind of data. Now, I do most of my work in Python, which is a great language for modern astronomy. It's interpreted, so you can just type and run. There's no compiling and stuff. There are a huge number of libraries available to help you do almost anything you'd want to do without doing very much coding. This view here is called IDLE, the Integrated Development and Learning Environment, and it's basically an interactive Python engine that you can type code in, and it will run it right there and display the results. You can ask for help on all the objects and functions, load libraries and so forth, and get directories of the contents of objects. So it's a really, really great learning tool. Next slide. The cool tool that I'm really enjoying is called the Jupyter Notebook. You'll notice Jupyter is misspelt, astronomically speaking. But basically, it's a browser-based, interactive, graphics-capable development environment. And it gives you a complete interactive record of the programming you're doing with the documentation and all the results. So you can debug on the fly, rerun code without having to type everything back in. And not only does it document your code for when you go back to it later, but you can also share it with others. So you have to install Python and Jupyter on your computer. You type Jupyter Notebook into a terminal window, and when Jupyter opens up, you ask for a new Python kernel, and up comes this empty Python or Jupyter Notebook. At the top, you can see this is an untitled page. Last checkpoint 33 minutes ago, so I haven't titled it yet, and it was last saved 33 minutes ago. So if we click on the title and type in a new one, we get next slide. You can see there's the title I've added to the workbook, and that also gets used as the file name on the disk. Two primary options in typing information into each little cell. It can be code, which is generally Python code, or you can put in what's called Markdown as opposed to markup. And it's basically just a very thin formatting language, somewhat like HTML, but it allows you to format the text, change colors, add lists and lines and so forth to really pretty it up. And so you type your code or whatever into the cell and you press Shift-Enter, and the notebook will run your instructions. Next, please. So the other thing you have to do every so often is you can see the little line of buttons just above the cell, and the left-handmost one is the save button. You just click and save, and you can see now up beside the title, it says last checkpoint a few seconds ago. So that tells us that we're up to date and have everything properly stored. Next, please. So we changed this cell to Markdown, put in 3 octothorpes, which basically tells the notebook how large a text font you want, and you put a title on the workbook, press Shift-Enter, page down. Or, sorry, next slide, please. And it puts in the title on your workbook. Next, please. So the next thing we have to do, I mentioned all these Python libraries that are available. Well, we want to use some of these libraries, so we type in import statements and so forth. In this case, we're using matplotlib, which is a library of plotting commands, extremely versatile and flexible. You can do all kinds of really cool publication quality graphs and so forth. We import light curve, which is a big library of light curve analysis tools. Very sophisticated stuff. Would be an extremely serious challenge to try and program yourself. And then we have a program called Pyriad. People who write Python code tend to stick a pi in wherever they can in their library names. What it provides basically is a graphical user interface to light curve, so we can do everything by clicking on buttons rather than having to type in commands. The AstroPy table library, it just helps us load and save data and divides our data all up into columns and everything, makes it very convenient. And AstroPy units, I don't think I actually use that in this one, but it basically handles all the units. So if you have units on your data like electrons per second, furlongs per fortnight, you can input a table of furlongs and another table of fortnight, divide one table by the other, and it will keep track of the units, automatically convert to other units that are maybe more useful than furlongs per fortnight. So we hit Shift-Enter, and next slide. And you can see it's now run that code, and those libraries are all now available. So we put in some actual functional code of our own. First, I define the name of the data file that I'm going to be using. And then I use table.read to load this table into the machine. And then the last line data table basically displays what I've just loaded. So next, please. And you can see at the bottom there, the start of the table. Next, please. So here's the table summary that you get, first 10 lines and the last 10 lines. There are 2 columns. HJD mobs is the heliocentric Julian date at the middle of the observation. And the second column is the basically the brightness of the star in comparison with the ensemble of other stars that I was measuring. Next, please. So we take our table and let's see, we take the first column and assign it to a variable called time. We take the second column and assign it to a variable called flux, and then we pass those 2 variables into the constructor for a light curve. We take the resulting light curve object and we pass it to Pyriad. Now we have a Pyriad object. Next slide. And up comes the graphical user interface for the package. consists of 4 tabs across the top. The first one up is the time series. So this is actually a plot of all the observations. You can see several hundred observations on each of the 19 nights. Because it spans 3 months, of course, each night's observations are all jammed together. So next slide, we can zoom in on any section of that plot. And here's the data from one night. Next slide. So the next tab over is called the periodogram. And what's happened here is the light curve software has tried to fit sine waves to all of my data. And it's tried thousands and thousands and thousands of different sine waves and then measured how well each one fits the data. And that then is displayed in a plot called the periodogram. And so this is basically just a graph of how strong the signal is at each frequency. Oddly enough, frequencies are done in microhertz, which is kind of a little hard to get your head around. But anyway, next slide, please. So we can zoom in here as well, and you can see that this periodogram is quite coarse. There's lots of fine detail, but the light curve has determined the strongest signal and marked it with a black dot, put the frequency in the little text box near the top with its amplitude to the right. In this case, this is about 110 microhertz. So that's about 1/9,000th of a cycle per second, which means the period of the star is about 9,000 seconds, which is about 2.5 hours, as we expect. And this is actually rather on the short end for high amplitude delta Scutis. But we click on the green Add to Solution button, and then click on the Refine Fit button next to it. And next slide. What it's done now is it's taken that sine wave, subtracted it from all my data, come up with what's called the residuals, done a new fit of thousands of sine waves to it, marked the strongest signal, put that signal in the little box. So we're all ready to pick up our second frequency. But before we do that, next slide, let's go back to the time series. So here you can see the 110 microhertz sine wave, and it's definitely phased pretty well with that night's data. The maxima appear roughly where they should, and the minimum. The amplitude is wrong. So it's not great, but at least it looks like we're probably heading in the right direction. So next slide. We can also go over to the Signals tab, and this one keeps a table of all the various frequencies that we've added to our computer model of the light curve. And you can see it also has the next strongest frequency, the 132 microhertz, has an Add to Solution button and a Refine Fit button. So we can add our new frequencies without having to go back to the periodogram or the time series. Next slide. So here we've added the second frequency. And what happens when you do Refine Fit here is it actually takes both the frequencies and redoes the fit for both of them simultaneously. So each of them changes slightly so that they better fit the data. Next slide. And now you can see, even with just 2 frequencies, you can see the fit to the data is dramatically improved. There's clearly still a slight problem on the first maximum and a more significant deviations on the minimum. But, you know, basically we've gotten an awful lot better than what we had before. Next slide. So you can see here I've added 4 more frequencies, and the question is, when do we stop? This program will let you keep adding frequencies almost ad infinitum. So there has to be some way to know when we should quit. Next slide. Basically, the software has a significance measurement. What it does is it looks at the noise surrounding every point on the periodogram and decides what's the noise level and what's significant data. And you can see in this case here, it's added the little red dashed line. Anything below that is probably just noise, and things above that are significant frequencies that are probably useful. Now, in this case, you can see the strongest frequency marked is it's about 373 microhertz, and it's above the little red line, so we can add it. If it was below the line, then we would not add it. Basically, what we would be doing is we would be starting to fit the noise in our data rather than the actual useful information. Next slide. So here I've run through and come up with 8 frequencies total that all have significance. And once I've added those 8, all the other peaks drop below the useful significance line. So this is the point at which I quit. And next slide, you can see now the light curve is even better fit, even the little errors at the minimum and the peaks and stuff. Well, other than the errors in my photometry, the light curve basically is fit almost perfectly. And next slide. So the last thing we do is we use fit values function to print out the table, and then we can save it to a file on disk, and then open it up, for instance, in a spreadsheet or whatever, and start to look at it and see what's going on. So next slide. So this is the table of the frequencies I got and the errors on the frequencies. And I want to draw your attention to how small the errors are compared to the frequencies. The top 2, this is about 3 parts in a million are the estimated errors on these frequencies. So on our 2.5-hour period, we're getting an accuracy of about 25 milliseconds. And even down at the bottom of the list, where these are very small amplitude signals, you know, just a few thousandths of a magnitude, we've still got accuracies of around 2 parts in 100,000. Next slide. So we have all these frequencies, and what do they mean? Well, it's very interesting once you start looking to realize that the first 2 are, I've called them F0 and F1. All the remainders are all linear combinations of those 2. F0 plus F1, F1 minus F0, 2 times F0 plus F1, and so forth. So I think what basically this means is that they're kind of like harmonics. You think of like a violin note has a fundamental frequency, and then there are harmonics above it that give it the sound characteristic of a violin. So these are the similar ideas. It's just that with 2 frequencies going, they combine to form all these extra frequencies. Next slide, please. Now this is going to be challenging. This is I've been trying to figure out how to present this, but you can sort of imagine this is actually for an organ pipe. This is the air motion inside an organ pipe, which is open at one end. And you can imagine this blue box. The first, we'll do the one on the right. And imagine that it's the surface of our star. So the surface would be at the top of the box, and the layer at which the temperature gets to be about 40,000 Kelvin would be at the bottom of the box. And then the spacing between the two lines, the two colored pinkish and orange lines, basically tells you how far up and down the surface moves when the star pulsates. So you get maximum motion up near the surface, and then down about the 40,000 K level, there's no motion at all. Now, this is called the fundamental mode, and this is what most variable stars pulsate in, and we call that, we give it a period of P0 is the label that we put on it. Now, in the middle, what can happen sometimes is we get what's called the first overtone, where the outer layer of the star, so again, 40,000 K at the bottom of the blue box and the surface of the star is at the top. The outermost layer is actually moving outwards while the lower half is moving inwards. And then when the lower half is moving outwards, the top half is moving downwards. And this is called the first overtone, and we label its frequency with P1. If things get really extreme, you can actually get two nodes. So at the node where the two lines cross, there's no motion of the star. So, and the other thing I should mention is the fundamental and the first overtone often occur together. So you get stars that are pulsating in both modes at the same time. So the left-hand box is the second overtone. There's a top layer that's moving out while the middle layer is moving in and the bottom layer is moving out, and then they reverse directions. And there are two layers within the star that are not moving. And in theory, we can continue on to the third overtone, the fourth overtone, and so forth. Except those kind of things hardly ever happen. Next slide. So the ratio of the two periods or the two frequencies that I've determined is 84%. Now, in these kinds of stars, we have the first overtone at P1 divided by the fundamental frequency P0 is almost always very close to 78%. You can get stars that pulsate in the first overtone and the second overtone, or the fundamental and the second overtone. But in that case, the second overtone frequency or period divided by the fundamental period is 61%. The second overtone period divided by the first overtone period is 78%. So what happens with the third overtone? So now we've got four layers in the outer part of the star that are moving in and out, and three layers that are also moving in and out at the same time. And the ratio of the third overtone to the second overtone periods is 84%, which matches our star. So as far as I've been able to determine, looking through the literature, this is the only star that's been found that is oscillating in the third and second overtones, not pulsating in the fundamental or the first overtone, just the third and second overtones. So this is, as I say, as far as I can tell, a unique star. And so I've been in contact with an astronomer at Los Alamos National Laboratory, and I shared the data on this star and several others with her and her team. And they are working to run a numerical computer model to see if they can get the computer to simulate these pulsations. And I will keep you updated as that progresses. Next slide, please. So I hear you're saying to yourselves, well, Rick, I don't have all this data. In particular, I don't have 4,000 data points on a star. So is this useful? Well, there are some other great data sources, all publicly available, of photometry of stars. The All-Sky Automated Survey for Supernovae has years of data. Now, the difficulty with it's Earth-based, small telescopes, 100 millimeter, actually super duper camera lenses, but they observe the whole sky, and so you'll get 1 or 2 observations per night of your star. And of course, being ground-based, they're not stupendously accurate. It's just very nice data. Another option is the Kepler satellite. If you recall, that was the exoplanet searching satellite, viewed a small area, square in between Lyra and Cygnus, and it basically stared at the same square sky for several years. So if the star you're interested in happens to be in that field of view, or if you're smart enough to pick a star that is in that field of view, you get extraordinarily accurate photometry, like down in tens of micromagnitudes, and hundreds of observations. I think it's 120 per hour, continuous for up to about 3 years. And the last and most current option is the Transiting Exoplanet Survey Satellite, which is still in operation. And it basically observes big strips on the sky, and observes for a month, and gives very good, exceptionally good space-based photometry for about a month, and then it moves on to the next strip. So you get, as I recall, something like 12 or 15,000 observations on a star. And then as it moves around the sky, eventually it will come back to the same strip, and you'll start getting more data. So this stuff is all easily downloadable. The light curve package was actually designed to analyze Kepler and TESS data, so it's got all the tools to download that photometry. And this is a very popular business, even among small-time professional astronomers, is searching through these catalogs and looking for exciting stars. So you can do this work at home, even if you don't have a telescope. So that's all I have, if there are any questions.
Great, thank you so much, Rick. We look forward to hearing an update on that star you're discussing with those folks. We have a couple questions from Mick. First one is, you could have mentioned you were doing Fourier analysis, which I think many of our folk would have at least heard of. Why not give them that tag?
Right, good point. Thank you.
Another one, are your photometer values actually precise to 10 to the -5?
No, the measurements that I'm doing, the brightness of the star is probably 3 or 4 thousandths of a magnitude, and the timing on my data is probably good to maybe 1/10 of a second or somewhat better. But the thing is that since I'm measuring this light curve over about 1,000 periods, if I can measure the peak of a curve to within, say, 60 seconds, then over 1,000 periods that gets reduced down by a factor of 1,000, so thereby improving the accuracy.
Okay, and then last, could Rick post his Jupyter notebook?
Sure, I could do that. I'm not sure where, but I'll figure out how to do that.
Okay, great. Thank you so much, Rick. Appreciate
All
that.
right.
All right, now we're going to slide into our observation reports, and we're going to kick off with Bob.
How do you do? When I first started imaging, all my data was tossed into whatever folder happened to be open. This work will work for a short while, but soon everything becomes a gigantic mess. I quickly realized that I needed some organization. Next slide, please. Now, when I collect data with my telescope, the raw data is stored in my computer by date. I try to funnel this date-organized data into directories that are organized by target names. Next slide, please. Within the organization of object names, the files are organized by date. When this transfer between raw data and process data occurs, I like to calibrate the image files. This includes applying bias, flat, dark frames to the images while removing any hot pixels that I know about. I try to label these directories with cal BP to remind me that some processing has already been done. Next slide, please. So can you go back one, Chris, please? So when I was organizing my M51 data from last month, I noticed that I'd been imaging M51 for over 2 decades. A quick look at my directory showed that I had pointed my telescope at M51 75 times and had over 3,000 individual pictures. Wouldn't it be interesting to see what an image that combined all this data would look like? I arbitrarily decided to go back to 2009, which would give me 14 years of data. This included 2,273 images. I checked each image for obvious mistakes like satellites, clouds, and bad guiding. This process was incredibly tedious and took 2 days. I rejected 870 images, which left me with 1,403 for my final M51 stack. Aligning and stacking 1,400 images is not a trivial task. Next image, please. The first obvious problem is that I'd used different equipment over the years. My very early images were not guided and my mounts weren't great. When I upgraded the mount and started guiding, my star images really improved. Over the 2 decades, I have transitioned through 4 different cooled astronomical cameras. These had different size chips and different sized pixels. Next. In my first camera, the Cookbook CCD, the pixels were not even square. This camera came as a kit with a book of instructions written by Richard Berry. You assembled it yourself. About 3,000 of these cameras were made. Next. This camera was primitive, but not terrible. Here's a photo of M51 taken with a Cookbook camera in 2008. I was using a CCD camera 2 generations newer at this time. I took this photo on a challenge by the author, Richard Berry. Next slide, please. One big problem is camera color sensitivity, differences in sensitivity. My present camera is equipped with a color corrected filters which produce white stars when red, green, and blue are combined equally. This was not true of my earlier cameras. Next. I have also used several different telescopes, sometimes with reducers and field flatteners and sometimes without. These telescopes and their accessories combined with different CCD cameras give images with different fields of view and different fields of curvature. Next slide, please. Field curvature is the hardest problem to deal with. Interestingly, refractor and reflector telescopes have fields curved in the opposite direction. We tried to correct this with field flatteners. These are lenses designed to introduce the opposite curvature of the telescope, but just enough to flatten the field. Field curvature does not matter when you look through a telescope, as long as it's not too extreme. But since CCD cameras have flat sensors, field curvature matters. Most astronomical image software makes the images bigger and smaller, and then rotates the images so that the stars of all the images are one on top of the other. This works very well with all the images that are taken with the same telescope and camera, and the telescope is pointed at the same target. It does not work well if the telescope and camera have changed or the camera is not pointed at the same target. For example, you are taking a mosaic of the sky and the telescope is pointed at different parts of the sky. Then you cannot match the stars. Next. Since my images are taken with all sorts of different telescopes and different cameras, I need a more sophisticated alignment program. This program needs to warp and stretch the images so that the stars lie one on top of the other. I am sure there are many programs that do this, but I only know of one, Registar. This program was written and sold by a Canadian company, Auriga Imaging. It might be the best alignment program written for deep sky astronomy imaging. But is it ever unfriendly? If you do go this right, be sure to read a few online tutorials first. I loaded my 1,400 images, and guess what? Either the computer or the program choked. Too many files. I divided the stack into 4 batches of 350 files, aligned these batches, and stacked them. Then I aligned and stacked the new stacks for my final image. Next. I use Registar to align the images, but for stacking and color combining, I use MaximDL. This program was written and sold by a Canadian, Doug George. His company is based in Ottawa, and he is an Ottawa RASC member. If you look at the long column of file names, you will notice the small boxes beside them marked with with a check or an X. These marks indicate whether or not the image was well focused and well guided. About 20% of the images were rejected using these criteria. That left the final image containing about 1,100 frames. Some of these frames were 10-minute exposures and some were 4 minutes. So the final image included about 120 hours of exposure time. Next slide, please. This is my MaximDL final stack. As you can see, the color correction is crazy. But that is what you get when combining images taken by cameras with wildly different color sensitivities. Next slide. Fortunately, the software can recalibrate the colors. We know that stars are generally white, and the background is generally black or dark gray. Click on the background, and then click on a star, and the program will automatically adjust all the other colors appropriately. This color correction usually gets you in the ballpark. Next slide, please. After cropping the image, slightly readjusting the color, and applying a small amount of sharpening, this is my final 120-hour image. I am generally pleased with this image, but was it worth staring at a computer screen for the better part of 3 days? I doubt that. It is without doubt the smoothest image that I have ever processed. It is hard to beat 120 hours of exposure when trying to reduce noise. There is also a fair amount of detail in the image, and it would be fun to feed the data into one of the more modern AI deconvolution programs. I think I'll point my telescope at another target for a while. Thank you very much.
Wonderful. Thank you, Bob. Appreciate that. All right. Richard, you're next.
Hey, coincidentally, I'm also going to be talking about M51. Anyway, these are some observations that I took at the RASC Ottawa's Star Party on the 22nd of July. I was demonstrating live stacking using my Astro camera and the William Optics Z73 telescope. So I started out first thing in the evening before it got totally dark by putting the lens cap on the camera and taking dark frames. So while people were gathering and coming around looking at all the equipment, I said, here I am taking pictures of nothing. And astrophotographers do a lot of this, and we almost never show them in public. because they're not really very interesting, but they are quite necessary to take these pictures of nothing so that you know what nothing looks like, and you can take it away from all of your pictures that have something in them. What you're seeing here is very greatly boosted in intensity. It would normally just look completely black, but when you boost the intensity, you see that there's a glow up in the mainly in the top right corner, but also down in the two lower corners. And this is coming from the heat of the internal electronics. It's called amp glow, amplifier glow. And it does start intruding onto the faintest objects that you're taking when you're taking real pictures. If you look closely at this picture, you'll also see a bunch of little dots. These are bad pixels that are not functioning correctly or getting a little bit of heat again, causing them to trigger. So we need to get all of these things from the dark frame and take them away from our proper light frames. Next one, please. After a while, and still while the sky was quite light, I put in another cap over the front lens, as this time a translucent cover on the front lens, so that I was taking a picture of more or less uniform brightness. But now there was light passing through the optical train. And this again is a picture of nothing, but it's a picture of the nothing that includes the lenses and the camera itself. And it's got a bunch of dirt on it. And this is unavoidable. We always get a few little dust specks, but when they're right very close to the camera sensor itself, they are completely out of focus. And so that's why they look like fairly large black circles instead of simple dots. So once again, astrophotographers take a lot of pictures like this. They call them flat frames. And again, we want to remove these effects from our pictures of real objects. You may also notice something called vignetting, which is the fact that the center part of the picture is noticeably brighter than the corners. And again, we can adjust all our other photographs to compensate for this effect and remove it. Next one, please. So once it did get dark enough, I started taking pictures of M51. The Whirlpool Galaxy up near the handle of the Big Dipper. So I was trying to make a compromise here between the length of exposure and how much patience my audience might have. So I chose 60-second exposures, and this is just one single 60-second exposure. You compare this with Bob Olson's stack of many, many, many hours of exposures. But this is what popped up on the screen of my laptop, and I could show the audience, oh yes, there's definitely an interesting object here. It looks like it has spiral arms, and then there's this weird fuzzy thing beside it to the right. So that caught people's attention, and they started watching for a while. And next picture, please. I kept live stacking. So every time another 60 seconds passed, another picture would be stacked onto the deck. And the picture started getting sharper, more contrast, brighter on the galaxy, darker on the background. And we could actually get quite a lot of detail coming out on M51. But you'll also notice down in the lower left-hand side of the picture, I don't know if you can point to it, Chris, but there's a little edge-on galaxy down there too. So there's actually three different galaxies here. There's M51, the main spiral. There's the other galaxy, which is nearby. Sorry, I don't have the number for that one. And then there's this other galaxy down in the corner, which is IC 4263. So that was the what came up towards the end of the evening after 20 minutes of stacking the photographs together. And I haven't done any subsequent processing on this picture. But if you go to the next slide, please. When I got it home the next day, I did put it through PixInsight and increased the contrast, did a bit of sharpening on the stars, and boosted the color contrast as well. So now you can see that definitely there are blue areas in the spiral arms, and the other galaxy to the right is definitely a more orangey red color. So that's my observations for from the star party. Thank you very much.
Great, thank you so much, Richard. All right, I think I'm up next. All right, so my first image here, I think I've got 4 images to show. My first image here is of NGC 4676, or the mice galaxies. Next slide, which I think, or yeah, if you go back, sorry. There was supposed to be a zoom in effect there, but maybe it's not working. There it is. So this is a pair of interacting galaxies in Coma Berenices. They're about 290 million light years away from us, and they've begun the process of colliding and merging. The nickname the mice galaxies come from the long tidal tails that the spirals have as they orbit each other, and that's caused by the differential gravitational attraction between the matter that is close to the mutual center of mass of the two objects and the matter that is further away. So anything that's close to the center of mass collapses in sooner than things that are farther away, which is similar to the maybe the effect of a comet tail. This image is composed of 187 3-minute sub-exposures, giving us a total integration of 9 hours and 21 minutes. This data was captured on May 14th and May 23rd through my 11-inch Edge HD Schmidt-Cassegrain telescope and using a ZWO ASI 2400 MC Pro color camera. Okay, next one. This is Messier 82, or the Cigar Galaxy. It's probably one of my favorite objects in the sky to image. It's pretty dynamic. It's got a lot of stuff going on. So M82 is a starburst galaxy in Ursa Major. It sits some 12 million light years away. It's about 5 times more luminous than the Milky Way, and its central region is 100 times more luminous than that of the Milky Way. The starburst activity is thought to have been triggered by a gravitational interaction with M81, which you can actually kind of see on the edge of the field along the left edge of the field. You see a bit of one of the spiral arms of M81 kind of sticking into the field of view there. An M82 contains the brightest known pulsar in the observable universe, designated M82X2, and that was discovered in 2014. So this particular image is composed of 45 sub-exposures in each of red, green, and blue, and 49 3-minute sub-exposures in hydrogen alpha for a total integration of 9 hours, 12 minutes. It was captured with a ZWO ASI 2600 Pro monochromatic camera through an 8-inch Edge HD on the nights of April 14th, 15th, and 16th. I think there should be a zoom effect too here. I think all my images have a zoom effect because I felt zoomy this time around. All right, next one, please. This is Messier 88, which is a spiral galaxy in Coma Berenices, some 50 million light years away. You may as well hit the zoom effect now. It's one of the 15 Messier objects in the Virgo cluster of galaxies. It's classified as a type 2 Seyfert galaxy, which means it produces a very narrow, specific spectral line emission from highly ionized gas in the core of the galaxy. This image is composed of 35 3-minute blue subs, 31 3-minute green, and 20 3-minute red sub-exposures for a total of 4 hours, 18 minutes. I did want to get a lot more data on this, but skies were pretty cloudy ever since I took this image, and now it's a little bit too low. This image was taken on March 28th with the same setup as the previous image. So the 2600 Pro mono camera and an 8-inch Edge HD. Next one, please. So this is Messier 64, or the Black Eye Galaxy, which is a spiral galaxy some 17 million light years away in Coma Berenices as well. So there's a dark band of absorbing dust that partially covers some of the core of the galaxy, and that's where this galaxy gets its name of the Black Eye Galaxy. It kind of looks like it has a black eye. The interstellar medium of the galaxy, so sort of the gas and the matter that isn't stars in this galaxy, is composed of two counter-rotating rings. So the rings actually rotate in opposite directions with respect to each other. It's the inner ring that contains the very prominent dust lanes. And despite the fact that the interstellar medium of this galaxy is composed of two counter-rotating rings, the actual stars in the galaxy don't seem to have the same effect. Like they're all the stars in the galaxy seem to be rotating in the same orientation. In this image, I also captured some of the IFN, or the integrated flux nebula, which is kind of that sort of wispy cloud-looking effect surrounding the galaxy. So I believe that's all dust and gas that's sitting just outside of the Milky Way and just coincidentally in between us and M64. So this image was composed of 43-minute subs in each of RGB and 99 3-minute subs in luminance, for a total of 10 hours, 57 minutes of exposure. Also through the 8-inch IGHD and the ZWO ASI 2600 mm. Cool, that's it for me this month. Next.
Well, hello, everybody. Some of my favorite summertime deep sky objects are in the constellation Sagittarius. This is Messier 8, the Lagoon Nebula, captured from my downtown balcony using the Sharpstar 94mm refractor with a Mallancam Skyraider camera. I use the Optolong L Extreme filter for light pollution and also to capture the hydrogen emission caused by a nearby young and massive star named Herschel 36. This is a stack of 12 10-second exposures post-processed using Topaz Studio 2. Next one, please. And here is a view of M16, the Eagle Nebula, taken with the same equipment and similar exposure time. M16 is part of a diffuse emission nebula containing several active star-forming gas and dust regions, including the pillars of creation that you see in the center. M16 is approximately 5,700 light years away. Next one, please. And here is a view. Okay, now we're moving to the constellation Cygnus. And I wanted to take a good look at the Cygnus wall, which is represented as the southern portion of the North American Nebula. This area in the lower right portion of the image exhibits the most ionized gas and concentrated star formation in the whole nebula. The Cygnus wall spans about 20 light years and is approximately 1,500 light years from Earth. Next one, please. And moving southeast past the star Saturn in the constellation Cygnus is NGC 6888, the Crescent Nebula, which is an emission nebula energized by a fast stellar wind from a nearby Wolf-Rayet star named WR136. The Crescent Nebula is 25 light years across and approximately 5,000 light years away, and was discovered by William Herschel back in 1792. Thank you.
Great, thank you, Jim. I believe we've got Paul next.
Oh. Thanks, Oscar. I'm just going to turn off my video to make sure I try to not stall my bandwidth. You doing okay there?
Yep.
All right. Well, good evening, everyone. I hope no one got too zonked by that nasty piece of weather that moved through Ottawa yesterday. Our region certainly has taken some weird weather whacks this year. But on the bright side, there have been some evenings of clarity, and one of those occurred last Friday evening with the advent of a late evening aurora. I became aware of this through the space weather site, and Andrea also sent out a notice to inform our members of it. With an 85% moon up and some lingering clouds in our area, I was a bit skeptical about seeing anything special. And when I set up my camera for some focusing shots, I was even less encouraged. Mind you, the moon and passing clouds made from previous slide, please. Thank you. The moon and the passing clouds made for some nice views of lunar crepuscular rays beaming through the gaps. But the clear portions of the sky were very bright. This particular view was taken with my Canon 70D and Bauer 16mm lens at f2 and was a 2-second exposure at ISO 3200, basically facing south. Fortunately, the clouds were moving down from the north and heading south with a goodly amount of clearing already visible to the north. Next one, please. So this image is a 360-degree all sky view taken not long after shooting the previous slide. The clouds had moved away, and now the sky was even brighter, actually. With no clouds to obscure the moon. This image was taken with the Ricoh Theta X and was a 20-second exposure at ISO 640. It shows just how bright the sky was and how the moon was lighting up the fields and road at my campsite, which is what you see wrapped around the outside of the bright sky view. What it also captured, though, was a surprisingly bright aurora with both green and red components showing up, and you can see that in the north. I've labeled the cardinal directions there because this image can be a bit confusing if you haven't seen these all sky views before. So the next slide, please. Not sure whether it's my video or whether it hasn't advanced.
Looks like it hasn't advanced to me.
It has not?
Has not.
Okay.
Chris?
Chris, you there? Uh-oh. Have we lost Chris? I think we may have lost Chris.
I think Oscar, though, he made you able to advance, like co-host, so maybe.
Oh.
Oop. Maybe you can now be the host, Oscar.
Maybe, except I may not have the slides. Let's see. Maybe I do have them here. There. Okay. One second.
We are just full of glitches tonight.
Yeah, I was not prepared for this. Okay. Let's share.
Okay, we have that one back. No, that's not the right one.
No, that is not the right one.
That's, yeah, so the next one after that.
There we go.
Okay, thank you. So this is, where am I here? I'm just checking my notes. This particular image is just a crop from the previous all sky view that I showed you, and it reveals the extent of the aurora in a more normal perspective. The width of the display ranged from about 60 degrees to at times almost 90 degrees in azimuth, and unexpectedly, it was visible to the naked eye, not just my cameras. Next one, please. So while the Rico Theta X was busy taking all sky shots, my 70D was pointed at the brighter regions with the 16 millimeter lens. The width of the field here is 70 degrees and the height is 50 degrees. This is an uncropped view and shows the red tips of the aurora reaching almost to the top of the frame at an elevation of about 43 degrees. This was a 4-second exposure at ISO 3200. I couldn't shoot much longer than that because the moon was still very prominent, and at the bottom of the frame you can actually see how it lit up the field that was at my site. At any rate, I shot a continuous sequence of such 4-second frames, 436 of them to be exact, to create an 80-minute long time lapse covering the best interval that the display was visible from my location, from about 1:45 to just after 2 o'clock, 2:05 in the morning. This time has been compressed to about 40 seconds, and then the sequence repeats. So if you can run the next one, Oscar, there, that is the time lapse. You can see how, as I say, you can see how the moon lights it up. The sequence should loop, actually. Nope. Previous one, please. Yeah, thank you. It'll loop just because it is fairly short. You can see how the moon is lighting up the fields, and the fluctuations in brightness were caused by a few cloud stragglers temporarily blocking the moon. You can also see the Big Dipper's motion during that 80-minute interval. What was really noticeable was the aurora's continual apparent motion from left to right and its rapid variation in brightness from moment to moment, with bursts of enhanced activity creating tall, bright red rays that were actually pretty easily visible to the naked eye. I was really surprised with this because of the brightness of the moon. So all in all, it was a very surprisingly nice show, much better than I thought it would be with that bright moon sharing the sky. Okay, next one, please. So the next few slides I have were the ones I was just originally planning to show tonight until that aurora happened last Friday, and Chris let me sneak in the shots that I've just shown you. Anyway, these slides are a sampling of some of the imagery I shot last month. I was away for most of July on an extended road trip out to British Columbia, covering some 11,000 kilometers in 26 days. Part of that journey was shared with my longtime fellow traveler of the night, James McQuaig, and that's him and I watching a diffuse aurora while camping at the Sleeping Giant Provincial Park up near Thunder Bay. This is a 360-degree all-sky view taken with the Rico, as I showed you previously, and is a 40-second exposure at ISO 1000. It's quite a contrast to that similar view I just showed you of last week's aurora here, taken with the same camera. The clear moonless sky allowed a much longer exposure and caught not only the aurora, but a horizon-to-horizon Milky Way, as you can see. All right, next one, please. 4 days later at Dinosaur Provincial Park in Alberta, we ran into a fairly active thunderstorm. This image was also taken with the Rico Theta X and is a 60-degree exposure at ISO 100. I caught this bright bolt of lightning seemingly wanting to reach down to my friend James's tent and give him a jolt. Fortunately, it was out past the silhouetted ridge that you can see here, but still rather close for comfort. Based on the timing of its very loud thunder blast, the bolt was just under 1 kilometer away. So yeah, that was quite close enough for my liking. Next one, please. So on the return leg of my journey, I stayed at Douglas Provincial Park in Saskatchewan. There I was treated to something I'd never seen before. From my campsite, I noticed this odd structure. At first, I thought it was a jet contrail, but when it didn't drift much with respect to the background stars and then started to noticeably fluctuate in brightness, both dimmer and brighter, I knew it was something else. I could only think of two possibilities: either a rocket contrail or a phenomenon identified only a half a dozen years ago. Could this be an apparent apparition of the phenomenon known as Steve? I haven't found any mention of rocket launches over this region, and it certainly didn't look like any I'd seen pictures of. Steve is an aurora-like phenomenon, but is not an aurora. Steve is actually an acronym for the Strong Thermal Emission Velocity Enhancement. And unlike true aurora, it's caused by a ribbon of hot plasma at an altitude of about 450 kilometers or so. Such a ribbon is typically around 3,000 degrees Celsius and flows at a speed of 6 kilometers per second. It typically only lasts about 20 minutes to an hour and almost always occurs in the presence of a true auroral display, although it's usually further south. Excuse me. This image was taken with the Canon 70D and 16mm lens and is a 15-second exposure at ISO 3200. Next slide, please. So one oddity I noticed with this phenomenon is that, and I'm still investigating this, is the noticeably reddish hue. I don't know if you can see that, but depends on your monitor and your color settings, but there's a noticeably reddish hue off to the left side of the ray itself. And I labeled the stars here just to give you the stars of the summer triangle here, just to give you a bit of a reference to what part of the sky you're looking at. And indeed, north is to the left of this particular frame. So this bright ray seemed to be associated with a general reddening of the sky towards the north and to the left of its of the ray itself, as you see in this frame. So when I didn't notice that reddening until I wound up processing the image. The ray was visible to the naked eye, but the reddening was not. But at the time, I did turn my camera to the north, and this is what I saw and caught. Next one, please. So this aurora was the brightest I've seen in a long time, and some of its rays reached to the zenith. It continually pulsed in brightness, and its form morphed noticeably and continually in very short periods of time. Next one, please. I did manage to capture a short time lapse of this aurora before it quickly began to change into just a bright but diffuse glow. This is only a set of 18 frames of 10-second exposures and spans a duration of only 6 minutes. You can see how active this thing was. This was all easily visible to the naked eye, including the colors. Even traces of the blue, and certainly some of the mauves and reds there that were visible. It was quite stunning. All in all, I mean, this was just fascinating because it morphed in such a short period of time that I don't think it's been probably 20 years since I've seen an aurora that has moved and changed that quickly. It was fascinating. That's it for me this month. I'll be doing a full presentation on my trip at October's meeting, when I'll have lots of images to share. In the meantime, I'm wishing you all clear skies and good luck with the Perseids tonight and tomorrow if you venture out to try to see them, and if we have some clear skies. Catch you next month.
All right, thank you, Paul. I'm going to hand the AV back to Chris, because he's rejoined us here. All right, and up next we've got Andrew.
Okay, hello, good evening. So can you see me?
Yes, we can.
Excellent. So recently, Paul Quaninger gave Taras and I some training on the new Meade telescope at FLO, the Paul Commission Memorial Scope, 14-inch SCT on the fork mount. And we've been learning how to use it and giving some feedback. And I have been very keen on attempting to track the International Space Station. This particular type of mount enables you to do that because it's has the ability to change its tracking rate while moving, which is not a common feature at all. And now this video was taken with a simple DSLR because my first attempt was with a smaller chip and I had some issues getting into the frame. But as a consequence, we have captured our live interactions and our emotions, and I would like to share that with all of you tonight because I think it's pretty exciting what this scope can do, and I would encourage other people to try it. The software that I used was pretty old at the time, originally developed by an individual who passed it on to a new group of people and can be found at heavenscape.com. My ultimate goal will be to get some better exposures, but for my second attempt, I think it's quite admirable, and I hope you all enjoy it. If you could please play the video now, it'd be great. Excellent. There should be sound with this. Okay.
And you got it almost at the highest elevation.
I got it. Got it.
Is it there?
Still there. It's near the edge of the... Come on,
Oh, it's
stay
very
with me.
bright.
Stay with me. It's going away.
It's in the
Sorry, I'm going... Maybe I'm correcting it the wrong way.
I think you overshot it, yeah. Or the other way around. No. Come up.
Oh, look, you got a lot fatter. It's out of focus down there.
It's fading now. I think
Oh, it's back.
Yeah.
I got it.
Then just keep it that way. But don't overshoot too much. Maybe
That's not centered with the camera anymore, but... Hey, the moon! Oh! Oh, I got it! Yes! That's amazing!
Whoa. Well, it's as good as it gets.
It's gone now, right?
No, it's not there.
Yeah, I think it faded right as it crossed the moon.
Yeah.
Okay, so that was an amazing surprise for us as well. Was not aware that there was a near transit happening that evening. So that was like, could not have gone better, honestly. It was an exhilarating experience that will be very difficult to top, in my opinion. But I have to thank Paul for making this possible. Exactly, it's just photobomb. Yes, thank you, Paul, for giving us the access to the Meade telescope. It's a beautiful piece of equipment. It has a very long reach. It's a 3,556 millimeter focal length, which is one of the reasons I use the DSLR camera for the bigger chip to get it into the field of view. Aspirationally, I want to capture it on a smaller chip and get more detail. This was also a little bit overexposed, but man, I am super stoked with the results anyhow.
Totally
Thank
awesome,
you all.
Andrew.
Very cool.
Thank you.
Thanks so much, Andrew, for sharing that with us.
You're welcome. That is all. Have a good night, guys.
Cool. All right. So we're getting near the end here. Thanks everyone for sticking around. We're going to hop into our observing challenges here. Last month or the month prior, because I think we skipped July. The challenges were M94 and GC 6181, Minkowski 164, and the creator Cleomedes. This month's challenges are M24, or the Sagittarius star cloud in Sagittarius. It's a pretty big object, good binocular object, good wide field object. Next one, please. Our intermediate is IC 1318b, which is a bright nebula in Cygnus, also known as the Butterfly Nebula, just near Saturn. Next one. And our advanced challenge is Minkowski 192, or the Footprint Nebula, also in Cygnus. It's tiny, had only 8 arc seconds by 16 arc seconds. And last but not least, our lunar challenge is the crater Stevinus, which is an impact crater in the southeast limb of the moon. That's it. Those are our challenges for the month. That's M24, IC 1318b, Minkowski 1-92, and Stevinus. Yeah, this is the Fred Lossing Observatory. Not sure what to say on this slide. Oh, the fellow star parties. Our next one will be August 19th. That's coming up, I believe, next weekend for those of you who are here and not at Starfest, which is also happening next week.
Oscar, I'll just add something to this slide. We've never had a pattern of having rain dates for the flow star parties, but you see our success rate in the last 3 on there, and then the last many before that has been dismal. So we expect to start introducing rain dates this fall for these member star parties.
Thank you there. Our next public star party, August 18th, with a rain date of the 19th, and that'll be in the parking lot of the Diefenbunker or the Ottawa Public Library in Carp. We had one on July 21st, 22nd, I believe. It worked out, the first one of the year. And we've also got one scheduled, like I said, on the 18th, 19th of this month, and 15th, 16th of September. Our flow director, here's some of the folks that help run the club. Flow director Rick Scholes, Estelle, our librarian, Peter Schutt, our telescope loan librarian. We're looking for someone to run hospitality, and our RASC membership coordinator is Art Fraser. Thank you to all who attended, approximately 60 of you, and thank you to all the speakers and organizers. And any comments can be sent to Dave Chisholm there, I believe, meeting chair at ottawa.rasc.ca. Our next meeting will be Friday, September 8th, which is the second Friday of the month to take us away from the Labor Day long weekend that happens in the during the first Friday of the month. And yeah, we'd like to announce that we'll be returning to Chasm in November for in-person meetings. And I believe we will be running a hybrid meeting as well. We'll continue to run Zoom for those who cannot make the meeting at the museum. But after a couple of years away from our group, it'll be great to get back together at last. Just a few short months away. Next one.
That's it.
That's it. All right. Thank you, everybody. Sorry it ran late. We had some long talks, but all very enjoyable. Thank you very much, and have a wonderful weekend. And for those of you going to Starfest, let's pray for clear skies and a fun time.
We'll see you there.